Okay, cool. So the first thing we're going to cover is we're going to build on our concepts from like the last couple chapters where we talked about order of reactivity. And we are going to look at carboxylic acid derivatives. And so when we have the different carboxylic acid derivatives, all that means is that this group will be replaced with other heteroatoms that have their own groups on it then. So when we talk about reactivity, we know that ketones and aldehydes are more reactive because of less steric hindrance and things like that. But when we're comparing just different carboxylic acid derivatives, the main thing we want to focus on is what this heteroatom is. And so we have oxygen, nitrogen, a halogen, and sulfur. And we know that nitrogen is going to be less reactive than oxygen. We've talked about this concept a couple times, and we know that nitrogen will be better at donating its electrons. Therefore, this bond right here will be super strong. So that's going to be the least reactive, and that is still true. And I'm going to give these letters so it's easier to write out the order. I totally did not just skip a letter. All right, so C is going to be the least reactive. I'm going to put it at the end over here. And the most reactive is actually going to be this guy right here. So the reason it's the the most reactive, aka the least stable, is because it pulls the electron density over here really, 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 really hard, and it does not donate its electrons into the system like our other groups do through resonance. So our nitrogen and our oxygen will donate electrons through resonance. Our halogen is not going to do that. It's just going to pull the density away from the carbonyl. So D is the most reactive. C is the least reactive. And now we're going to go through and fill in the spots in between. So oxygen is going to be the next most reactive. And picking between A, B, and F looks a little bit difficult because they're all pretty similar. But we can see that F has this whole other carbonyl right here. And so this lone pair is essentially going to be going to either side versus, sorry for zooming in and out so much, for A and B, the lone pair is only going to one of the carbonyls. So there's going to be more electron density donated in A and B than there will be in F. So we know that this bond in F is weak. It's going to be super weak. And so F is the next most reactive. And then we know that A and B are approximately the same reactivity. So I'm going to do like this. And then the only one we have left is going to be E, which is our sulfur. And so if I zoom out, ta-da. And then someone said more donating equals more weak. Well, okay, so I'll just show it one more time, kind of what I mean, because that's not exactly how I want you to think about it. So the more electrons, or the more electron density you're able to donate, that means you're going to have a stronger bond, which is going to mean it is less reactive. So again, the more electron donating effects you have, the stronger the bond, the less reactive it's going to be. So in this case, we have the electrons being donated to both sides. So overall, there will be less donation happening to this side, which means this will be a weaker bond, which means this will overall be more reactive because this bond can break more easily. Does that make it a little bit more clear? Okay. So now that we have the reactivity order, we're going to go through and name these guys. We should know most of these already, so what do we call this guy? I want you guys to tell me. Carboxylic acid, exactly. Perfect, and what about this guy right here? Ester, perfect. And what about this dude right here? This next guy. What do y'all think? Is it an amine or an amide? Amide, perfect, perfect. Alrighty. So these next ones are ones that maybe you haven't seen before. Do you guys happen to know any of these? If not, that's okay. We can go through it, but I just want to give you guys a couple seconds to see if you know any of them. Ooh, someone got one of them, which is the acid halide, correct? So that is the general name. If we had a bromine here, it would be an acid bromide. If it was a chlorine, it would be an acid chloride, so on and so forth. So awesome job, Catherine. So next up, we are going to call this guy a thioester. Thio for the sulfur, and it looks just like an ester, so we're going to call it a thioester. For the next one, this general kind of structure where there's two carbonyls and an oxygen in the middle, we're going to call that an anhydride. And this one specifically, since it has a CH3 and a CH3, we're going to call that an acid, I'm so sorry, guys. We're going to call it an acetic anhydride. So again, this general structure where there's an oxygen and two carbonyls, we're going to call that an anhydride. This one specifically is called an acetic anhydride because it has two methyl groups on either side. And we call that acetic anhydride again. And the reason I say that a couple times is because this one is very popular, and he does tend to ask you about acetic anhydride. Any questions on reactivity so far? Alrighty. So if you guys have any questions, say it in the chat. I will be looking through it. In the meantime, I want to tell you guys one last thing about reactivity. So when we are doing reactions in chapter 17, the goal of them is to essentially go from more reactive to less reactive. So we want to make a more stable product than what we started with. So what this is saying is essentially nucleophilic acyl substitution reactions, aka the reactions in chapter 17, typically go from more reactive to less reactive. And this is telling us that we're going from a less stable molecule to a more stable molecule. So for example, if I started with a thioester, what could I make in order to make a more stable product out of the list here? We can also rephrase that as, which one of these guys is more stable than a thioester? The amide, exactly. We can also, no, never mind. I was going to do another example, but it seems like you guys got the idea. One thing I do want to mention is that the acid halide is going to be so reactive. You are not able to make an acid halide via nucleophilic acyl substitution. I can say that one more time. Acid halides are so reactive that you cannot make an acid halide via nucleophilic acyl substitution reactions. Any questions? Anyone want me to repeat that? All right. So here in the corner, real quick, I will make a new page. Just make it easier. So just to reiterate, acid halides are going to be so reactive that you cannot make them via nucleophilic acyl substitution. The only way, you know what, I'll just go this way. So the only way you can make an acid halide is when you start with a carboxylic acid and you use one of those lovely reagents we did in chapter 12, either 11 or 12, such as PBr3, PCl5, and that whole group of reagents. Those are the two main ones. We can also use PCl3. So the only way to go from something to a alkyl halide is through these guys. Not through a nucleophilic substitution reaction. This is the type of question he likes to ask you, so please keep this in mind, and if you have any questions, let me know before we move on. I'll give you all a second. And yes, someone asked me to repeat it, so of course I can. So an acid halide is going to be so reactive and so unstable that you cannot form it through a nucleophilic substitution reaction. In order to form an acid halide, you have to use one of these reagents and react them with a carboxylic acid. So I'll write here, cannot make acid halide via nucleophilic acyl sub reaction. That looks like gibberish. There we go. Better? Are we all good? I wish you could send thumbs up emojis. I feel like I've said this before. All right. So, going back up here, we have to do one more thing before we actually go into our reaction mechanism and everything. We are learning how to name esters, and this is something that we may have very briefly touched on at some point, but for the most part, you guys haven't had much experience with this, correct? Okay, so we are going to, I'm going to zoom in real close. So when we are naming esters, we are going to always start naming on the side attached to the oxygen. And the reason for that is the side attached to the carbonyl is going to be our priority group, since it is attached to the carbonyl carbon. And this means that, as always, the priority group is going to have the end of the naming. So let me highlight them in different colors. So this area will be named first. And so please tell me what we would call this carbon chain. Pretend the oxygen isn't there. Just if we have 3 carbons in a straight chain, what would we call that? Propane, exactly. So we're going to call this propyl. And now let's use green. We are going to name this side. So what do we think that would be called, that group of carbons? Okay, so people said methyl, and I'm really glad you guys said that, because that is the trick that people always get mixed up on. So, yes, it looks like there's just this one methyl here, right? Don't forget this guy right here. This carbon is super important. Everyone messes that up, and usually he's able to trip you up on at least one exam question that way. Don't forget to include this carbon. So this is actually a 2-carbon chain, so we would call it what instead of methyl? Ethyl, exactly. So we're going to say propyl, F, and then last but not least, we're going to name this part of it. Does anyone happen to know what the suffix for a ester is? For an ester. If you guys don't know, that's okay, but I'll give you a chance to respond. Someone got it? Yes. Or a couple people got it, actually. Awesome. So it's O8. Exactly. So we're going to call it F, but we're going to say F and O8. Just because ethyl O8 kind of sounds weird. So we're just going to say propyl, F, and O8. Any questions? You guys good with this so far?
So what's that part called again? Like not as a part of the naming, but just in general?
So for which part? This?
Yeah, the yellow.
Yes, so the yellow is just O8, and that is the suffix for esters.
Okay.
Great.
Okay.
And then someone said, why is it in yellow? I don't know, I don't really know what you mean by that. I just highlighted like each chunk kind of, so you guys could see the difference in things. All right, so this next one, I'll leave it zoomed out a little bit for a second. So we know already that the suffix is going to be O8. So we'll leave that at the end. So we're going to name the part on the oxygen, my bad, the side on the oxygen first. So how many carbons do we have highlighted in red? Oh, I'm sorry, Abigail. I just understood what you said. So the "and" here, I just put in yellow. It should be with the green, but I had already changed my pen color and I didn't go back to fix it. So I will change that for you. My bad for misunderstanding what you said. But yes, back to this one. As you guys said, there are 2 carbons, and we would call that ethyl. So this is going to be ethyl something O8. And so how many carbons do we have on this side? Three, exactly. Awesome. So what do we call a 3-carbon chain? Propyl. Awesome. But for this example, we are going to name it. Wow. Hold on. I'm such a mess today. I don't know why I wrote that in green. It's supposed to be in red. And yes, guys, you're correct. It would be propan. Oh, wait. So in case anyone got confused by my mess of a color coding scheme, red here is the ethyl group. So that corresponds to the ethyl. The green is corresponding to those 3 carbons, which we will call propan. And then the yellow is our ester functional group, which we will use the suffix -08. So this guy would be called ethyl propanoate. Any questions on the first 2? I know I'm a little bit of a mess today, and I apologize for that. All right, if there's no questions, let's move on to this guy. And this one is slightly more difficult / complicated / easier to trip you guys up on. So let's start from left to right. How many carbons do we have on this chain? 4, and what do we call a 4-carbon chain? Butyl, exactly. So we're going to call this butyl. And the next chunk is the, I guess, ester functional group. So what is the suffix for that? -08, perfect. Alrighty, so now to the complicated kind of part is this guy right here. What would we call that? There's actually 2 correct answers here. Awesome, 2 people said isopropyl. That is one of the correct answers. So let me write down. And then someone asked a great question. Why isn't the red named first? So I'm just putting the names and then we're going to put them in order. Just because it, like, the chunk is a little bit weird. So I'm going to put them in order in a second. Sorry if that was confusing. I just wanted to like name left to right and then put it in order. So for the other way to name this, we are actually going to call this the parent chain, and we are going to call this guy a substituent. So if we name it like that, we would have 1-methyl ethyl. And you might be thinking, why in the world would we do that? That's gross. I agree, but that is the more correct IUPAC naming. So if we want to do the most correct IUPAC name for this, it will be 1-methyl ethyl butyl OH, but we're not going to leave the YL here. What are we going to exchange the YL for? AN, awesome. And if we put the first one together, again, as you guys said, the red will go first because that is the side on the oxygen. And one more time, we know that it's not going to be YL, so we're going to change the butyl to butan. So this guy can either be called isopropyl butanoate or 1-methyl ethyl butanoate. You guys should know how to do both of those names because Dr. West will usually ask you for this name, but he might say isopropyl and expect you to know what that looks like. I know I spent a little bit of time on these, but I just wanted to make sure that you guys are comfortable with these. Do you have any questions or comments or anything about the naming so far? I'll give it a few more seconds. So someone said, so the right side will always go first when writing. So don't necessarily think of it as left and right, because I have seen sometimes him give it to you like that. And then in this case, it kind of ruins that whole logic. Usually it will be drawn out like this, so I guess you can think of it as the right side, but it's better for you to think about it as the side attached to the oxygen and the side attached to the carbonyl. Does that sort of kind of make sense? Okay, cool. That's a great question, though. Alrighty. So now we're getting to my favorite part of this chapter, which is our nucleophilic acyl substitution reaction. And so first we're going to do a super general, basic, bare bones version of this mechanism, where we have a leaving group and a nucleophile and H2O. And the reason I chose to give you H2O is because that can act as an acid or as a base. And so in this reaction, in a nucleophilic acyl substitution, we're going to be able to pretty much always use acid and base equally and get the same product. So essentially what's going to happen in a nucleophilic substitution is the nucleophile will attack and kick up these electrons. For our intermediate, we're going to have something that looks like so, plus our nucleophile. And then we are actually going to go ahead and reform our double bond and kick off our leaving group. So we get double bond reformed, and now we have our nucleophile attached. And that is pretty much it for the basis of this reaction. Essentially, at the end of the day, all you're doing is taking away the leaving group and replacing it with your nucleophile. Any questions? I know it's a new mechanism, so you guys are probably like, so let me know if you have any questions or anything. If not, we're actually going to fill in a nucleophile and a leaving group, and we're going to do the reaction one more time. Alrighty. So let's say for a leaving group we have, I don't know, OH, sure, fine. Let's start with a carboxylic acid. And let's use NH2 as our nucleophile. And just for funsies, let's use HCl as an acid. So when we have an acid catalyzed, the first step is always going to be what? Protonation, exactly. And so what is the point of that? We are going to make the, yes, someone said it. We're going to make the electrophile more electrophilic. Awesome, yes, cool. All right, so I know I get way too excited. Don't judge me. Okay, so the electrons are going to attack the hydrogen and steal it. These electrons go back to the chlorine. So now, So now we get a positive charge here, and we have our OH chilling. So now at this point, our nucleophile can attack, and there's one thing that I want to kind of drill into you guys, because I see this mistake made, I don't know why that happened. I see this mistake made quite often, so I want to make sure you guys don't make that mistake. When we attack, we are using the lone pairs on the nitrogen to attack the carbonyl, right? So what we've been doing this whole time, it's going to look something like this, correct? So what this means is that we are always adding the side of the nitrogen. And I will show you what that means in case it doesn't really make sense verbally. So we are always going to add the side of the nitrogen and then have the substituents hanging out. Is anyone confused about why we added the nitrogen side to the carbonyl? If you are, please let me know. I see so many people make this mistake. Okay. Feel free to ask me at any point if you want to, or email me or whatever. Okay. So at this point, we have a charge right here. What is that charge going to be? When nitrogen has 4 bonds, plus, exactly. All right, so how do we get rid of a plus charge when we have hydrogens present? Proton transfer, yes. Intramolecular, yes. Okay, awesome. So now we have to think about which one of these OHs is going to get the hydrogen. Does it matter? No. Perfect. And the reason is because they are both OHs. I'm always going to use this one as the leaving group when we have 2 OHs just because I want to keep the consistency, but they would be the same. They're both OH. So with that being said, this hydrogen is going to, this oxygen is going to steal a hydrogen and give those electrons back to the nitrogen. And what's the point of doing that? H2O becomes a good leaving group. Exactly. So we're making a better leaving group. Perfect answer, guys. Alrighty. So we have a plus charge. And when we say that that's a leaving group now, which one of these, A or B, is going to form the double bond to kick off the leaving group? What do you guys think? And I can say the question again. So group A, the oxygen, or group B, the nitrogen? Which one do you guys think will form the double bond? Okay, so you guys all said the nitrogen so far. So if we use the electrons from the nitrogen to drop down and kick off the leaving group, we're going to form this guy. Oh, my bad. Supposed to be hydrogen. How do we feel about this guy? Good, bad, kind of like WTF. Not good. It has a plus charge, yeah. Overall, looking at that, you kind of feel like, ew, I don't really like that. So let's just try it. English is so hard today. Let's try it out with the oxygen. So if we did this, kick off the leaving group, we would get this guy. So we still have a plus charge here, but how do we feel about that guy now? Better. I agree. But why do you guys like this one better than this one? Anyone have any like reasoning or idea? Remember, there's no right or wrong answer. I just want to know what you guys think. One person said, or a couple people actually said, oxygen can hold the plus charge better. That's true. Yes. For the final answer, though, we are going to remove the plus charge so we can deprotonate both of them. But that is a really good logical reasoning kind of way to look at it. What else? First, I'll give you guys a hint. What is this thing called? What is that functional group? An amide, exactly. What is this thing? If you guys are just thinking, I have no idea, pretty much, that's what you should be thinking. We've never seen this guy before. He's super weird looking, super ugly. And if we think back to our order of reactivity, ignore this guy in the corner, we know that this one is the most stable carboxylic acid derivative. But this guy is a really weird looking thing that honestly doesn't look that stable to me. So which one would you guys go with? The amide or the weird thingy? Amide. Me too. Me too. I think that's a good idea. So let's move forward with that. So at this point, we want to deprotonate because you guys mentioned it has a plus charge. So how are we going to deprotonate? I'll zoom out so you can look at the whole mechanism. What do we have here to deprotonate? Cl-. Awesome. So the Cl minus is going to steal the hydrogen, give those electrons back. So we now have our final product, which looks like so. And you guys already told me, but I'm going to write it down again. It is an amide. Does this reaction sort of kind of make sense so far? Yes? Okay, good. So I'm going to write a little note here so that you guys can screenshot if you would like to. So that step will not happen because it forms an unstable product. And I'm going to go ahead and move this guy and then zoom out so you guys can, again, take a screenshot or whatever you would like. Ta-da! That's pretty much chapter 17 for you. You guys have any last questions, comments, concerns, anything like that? I'm going to send the attendance link once more, so please fill that out when you have a chance. And so just to review, like a 1-minute summary thing that I always do. Essentially, nucleophilic acyl substitution reactions are going to be, well, they're going to start out just like everything else we've learned, where if we have an acid catalyst, we protonate, we make the electrophile more electrophilic. If we have a base catalyst, it will make the nucleophile more nucleophilic by deprotonating it. And then we're going to have the nucleophile attack the carbonyl carbon. Eventually, this will cause the electrons from the oxygen to drop back down, reform the double bond, and kick off the leaving group. And then you get your final answer, where essentially all you do is replace the leaving group with a nucleophile. So on a scale of 1 to 10, 1 being this is super easy and 10 being this is the worst thing I've seen in my entire life, how do you guys feel about chapter 17 so far? Good, decent, 5, 6, okay. That's not too terrible for the first day looking at it. Someone said 7, that's fair. It does look pretty complicated and harsh just from our first look, but hopefully we can bring that down next week when we keep working on this. And we're going to do like 8 pages worth of practice problems. So hopefully after all that, you guys will feel like safe and secure with this stuff. On the agenda, I had put that we were going to start lactones and lactams. We didn't end up having enough time because I underestimated how long the reaction would take. So we are going to start out with this stuff on Monday. Any last questions, comments, concerns, anything before we end today's session? Oh, you guys are very welcome. You're very welcome. I hope that it's helpful. And I hope you guys have a great weekend. And yes, I can show the acid halide reaction. Here you go. Aw. Thank you, Rachel. You're so sweet. I'm glad I was helpful. Bye!